Welcome to today's Solenis Insight about Papermaking Industry 4.0, gaining more insight from the data you already have. I am Beth Ann Zarko, product marketer for Solenis's digital solutions, and I'll be your facilitator for today's meeting. I'd like to thank you all for joining us today. Before we get started, I'd like to cover some housekeeping items. Please keep your line muted during the presentation. We will have about 10 to 15 minutes for Q&A following the presentation. At that time, you can unmute your line to ask a question, or you can type the question in the message or chat window. You can find the chat panel by clicking the message icon at the bottom of your screen. There's also a raise hand icon if you would have a question. During the presentation, please feel free to type your questions in and we'll get to them at an appropriate time. This webinar is being recorded and a copy will be shared on solenis.com. Allow me to introduce to you today our speaker. Cydney Rechtin is Solenis's resident data scientist. She leverages her unique blend of paper manufacturing experience and data analytics to develop and support key analytical developments, including the OPTIX Applied Intelligence platform. Cydney holds a Bachelor's of Science in Chemical Engineering with a focus in pulp and paper technology from North Carolina State University and a master's in data analytics from Georgia Institute of Technology. At this time, I'll hand it over to Cydney.
Thanks, Beth Ann. And welcome everyone. Glad you guys could join today. Beth Ann kind of opened up the purpose and topic for this webinar. So after a brief introduction to the topic, we will get right to it by starting to talk about the process of going from data collection to value-added insights. We will discuss how to define your problem using data, how to set the foundation using predictive analytics, and adding on to that with some more advanced analyses. Analytics is really great, and we'll kind of talk about this throughout the presentation, but without proper implementation and adoption, a lot of the technical efforts are wasted. So we'll also touch on the topics of implementation and adoption. Now, I'm sure everyone has seen some of these buzzwords on the left here. There are so many in the industry around data analytics, but really at our core, we all just want to gather more valuable insights from the data that we already collect. We can use a combination of advanced analysis methods, but paired with interpretation from subject matter experts to get us there. The two together are really important. Today, I really want everyone to walk away with an understanding of what methods exist that can lead you towards doing more than just collecting your data. There are things that you're going to do in-house. We'll start with those basics, and then we'll share some examples and use cases as we work up to more advanced methods. Again, we will touch on implementation and adoption because it is arguably the most challenging part of creating value from these data insights. So defining the data or defining the problem using data, it is the first and foremost thing you must do when you are trying to solve a problem using data, because if the data doesn't support the fact that a problem exists, then we run into a few issues, and we'll kind of go into examples here. To all the manufacturers in the room today, or in teams, I guess you're kind of in your own room, this seems obvious. If you're culling paper for quality, or if you're suffering from variable raw material, you know that you have a problem. You're living and breathing it, boots on the ground every day. And in most cases, there's plenty of data to support that problem. On the screen, you'll see an example. Take this quality issue. Using one of the methods we'll discuss in a second, there's quite obviously a lot of material that is tested below the lower strength specification. So all of the blue squares to the left of the red line in the histogram chart, that is material that was made below specification limit. This is an issue that we'd like to investigate. We want to know why this production was bad. We want to know when it was bad. We want to know if it's going to affect our customers downstream and so on. Similarly, if you look at the chart on the right, another thing we'll go through in a minute, you might be investigating a customer complaint for low quality production in July, circled in red. That too is obvious in the data. That chunk of production is lower than the rest of the data, indicating that it is different than what you normally send your customer. But what if your data looks like this? So what if you tell me you're having a strength issue, and this is what if I plot a histogram, which we'll talk about in a second, this is what it looks like. Where is the data supporting all of the reels that you couldn't sell below the spec limit? Maybe they were downgraded and recorded as a different grade in the database. Maybe you can think of another common issue with missing lab data below a specification limit in manufacturing operations. But in any case, this is an issue we'd like to be able to investigate, but the data doesn't support the fact that a low quality issue exists. Almost all of this data is above that spec limit in red. So this would be quite difficult to analyze. We would have to get quite creative. So how do you define the problem using data then? I alluded to a few methods in the previous slides, and it's usually really easy to find evidence of the problem you're having in your data because, like I said, you're feeling it, you know it exists. And usually one of these three methods that you can do in-house will help you define the problem using data. And you really do have to define it first before you can start trying to solve it using data analytics techniques. So there are many, many methods, but the three that we're going to talk about today are the ones that you can do in-house. There are YouTube videos teaching you how to do these kinds of things in Excel. They're really base case things that your operations engineers can definitely provide you information on, maybe with a few minutes of exploring around in Excel and Googling on the internet. And they are histograms, percent stability, and a general variation trends. The easiest method is a simple histogram. So if you're struggling with something like low speed, low quality, wide variation, really a lot of different things, you should be able to visualize that issue in a histogram of something like your quality test, your production rate, the flow of something in your process. Simply draw up a histogram in Excel and interpret some of its components, such as the width, which corresponds to the variation, the distribution around the spec limits, which we just talked about earlier, the overall shape, which in most cases should resemble a bell curve, but not always. We won't get into those details. I personally always look at the histogram first because it gives me insight into the next two more involved procedures that we'll talk about. And the first of those is percent stability, which is on the right-hand side of this. If you don't really care to understand thoroughly the algorithm, it's okay, because really stability is just defined as the percentage of your production that is within statistical control. So you do have to calculate some statistical control limits. There's many ways to do this. On the screen, I've showed just a really basic blocking and tackling method. Again, the goal here is just to define the problem using data. But a process that is unstable is usually experiencing inconsistencies or recurring issues. So you would use stability analysis versus something like the histogram, or even the variation, simple variation technique we'll talk about next. If you're experiencing like whiplash, every 2 weeks you're having this problem, or every time you run this particular grade you're having this problem. So stability analysis is great for problems that aren't nearly as apparent as something like off quality. It can also help us, so if we have a distribution like we showed a second ago where there is no data below the spec limit, but we know we're creating material below the spec limit, instead of investigating the quality variable, you can use stability analysis to investigate something else that is highly related to the quality variable. Like, for example, maybe when you're in a poor production state, even if the quality data doesn't support that, maybe you slow back. So you can look at the speed of your production via stability analysis, or maybe you have an issue with a type of chemistry that you apply to your system. You can use stability analysis to look at that parameter rather than the actual issue that's causing you to have off-quality production. So it's important to note that you can be operating stably bad or stably good. So sometimes stability analysis isn't the best approach. If you're really consistently making bad production or really consistently running in this bad state, you might find that you have a high percent stability, which is good because you have really wide statistical control limits. So if your machine is experiencing unintended swings, maybe those swings will turn up when evaluating something different, like I mentioned, production rate or flow or somewhere in the process, because you've really got to get creative in choosing which data you look at. And you should really consult a subject matter expert to help pinpoint where to investigate. So remember, at this point, you're really just trying to make sure that the problem that you're experiencing exists in the data somewhere. Because once we prove that, the advanced analytics will do the heavy lifting to help you solve the problem. And we'll talk about that here in a second. The last and more involved approach I'm going to talk about today, and it's personally one of my favorite methods, is kind of a quick version of a variation analysis. I mentioned that there are so many ways to investigate variation. Any method that you choose is going to have some underlying assumptions that you need to validate. But for the simple purpose of looking for the presence of the problem that you're investigating in the data, I really like to use this quick and easy statistical process control approach. This is basic SPC methodologies for my manufacturers in the room who have dealt with SPC. You simply calculate the standard deviation from the data after removing some of the more extreme outliers, and you can plot that time series against those calculated limits. And this will help you identify off-quality production, swings, excess variation. It can help you understand if you're running stably very bad, and a lot more. This kind of chart is more involved, but you can still take away some of the key things that we were able to identify using stability and histogram charts. It's kind of the both of those mesh together. And I think visuals do a bit more, especially when you're trying to present this to the team of people who are going to help you try to solve the problem, whether that's your operations team or your local management team to get support in solving the problem. These more visual control charts tend to be very helpful. Okay, so you're experiencing the problem. You've successfully defined it using your data, but now what? The foundation of any of the advanced analysis we're going to talk about specific to the paper industry, but in manufacturing in general, is going to revolve around predictive analytics. And this is because in our industry, we have so much data being collected at a high frequency, and so many of those data sources themselves are interrelated. The most sophisticated methods to cut through that noise and help you actually digest the amount of data that you have is through prediction. So not just any prediction though. The data we have in the paper industry requires prediction methods that can support highly variable, non-linear, continuous time series data. These are all adjectives that describe how our data is quite different than e-commerce data or data for a bank to help determine whether or not they should lend you credit. Because our relationships within manufacturing and specifically the pulp and paper industry, the relationships in our data dynamically change with time. So if you're a manufacturer using predictive analytics currently, ask your supplier or your internal resource if they're using nonlinear predictive techniques with dynamic tuning using machine learning. And if not, it's time to upgrade, and you'll kind of see why as we finish out this presentation. With a foundation in predictive analytics, that is how we can move to the bigger, better things like real-time change detection, root cause identification, maybe closed loop predictive control. But before we get into all of that, let's see how predictive analytics has been used in our industry to create value. So what you see on the screen are just some details about a North American customer who's using a 30-second prediction of a common strength test in the papermaking industry. The prediction is built using novel methodologies that we just kind of tacked on that include some dynamic machine learning model tuning, and they update in real time so that as this customer's process changes, the prediction stays relevant. There's no need for a human to interact with the model at any time. This customer runs their basis weight in excess to ensure they meet their strength targets a lot of times. So we call this, they're running to an insurance policy. They're using more basis weight, which actually tends to lead to excessive strength, but they do it so that when they enter a period of upset, they don't make off-quality material. They know they have an opportunity for a 2% annual reduction in basis weight by improving their strength target adherence, so the amount of time that they adhere to their target rather than overshoot. So this real-time strength prediction allows them to optimize basis weight in real time. It gives them confidence to kind of nix that insurance policy so that they know when they're above their strength spec limits without having to rely solely on these periodic and highly variable lab tests. We all know that papermaking is not as simple as just move weight, see strength move, but this is why predictive analytics is so powerful. The prediction that they are using takes into account more than 200 of their process variables. I don't know about you guys, but I have a hard enough time thinking in 2 dimensions, add 3, 4, 5, 200. I can't as a human comprehend what that means. But the analytics methods behind predictive analytics knows that when one thing changes, it understands how that affects all of the other ones. And those relationships are ultimately captured in a predicted strength value. So it's really complex math, but it's really, really simple to interpret. Instead of getting a prediction test every 45 minutes from their lab, now they also have a prediction value or a strength value every 30 seconds from the prediction. A couple of more examples for our other North American customers using real-time predictions. In this case, these are both string predictions again. There's no true reason for that. It's just the examples I'm using. One was working towards a similar goal of basis weight optimization, but was also able to capture speed improvements. So you can see on the trend on the left that speed is going up and basis weight is going down. The other on the right-hand side was trying to optimize furnish because they struggled with this vicious cycle of making off-quality material, which increased their broke levels beyond their capacity. So they had a small to medium-sized broke tank. Anytime they made off-quality material, it was like a lot of off-quality. They filled that broke chest up, overflowing it most of the time. So they're sending fiber to the sewer because they're again adding more broke to the sheet to try to use up that broke capacity, which just adds to their strength issues, creating more off quality. So you can see this vicious cycle. This customer was able to use a real-time strength prediction to put more broke fiber in the sheet during good to normal production. So that alleviated this broke capacity issue they had in upset conditions while being more proactive in managing their strength. So in this case, this customer was able to increase their broke usage by 13%. And you can see they made like step ups. That's the bluish gray line. Maybe it's black. I can't quite tell. That steps up. And then the green line is the 30-second prediction. So as they're making these increased broke moves, they can see that their strength prediction is doing just fine. So it gives them that confidence. It removes the need for that insurance policy like we talked about earlier. So these customers are doing a great job using their predictions to drive value in their process. They're using less basis weight, they're optimizing their furnish, but once they latch on to these predictions, our customers often think of a million more questions that they want to answer using their data. And in our experiences, these questions that they have really fall into 4 categories of advanced analyses. And those are closed loop predictive control, change detection, root cause identification, and prescriptive analytics. Each of these can offer them some solution to the problems that they're asking us to dig deeper into. So for the remainder of this presentation, we're going to dig deeper into each one of these. So when a paper manufacturer is interested in incorporating predictions into their control schemes, APCs, or something else, they're looking for closed-loop predictive control. So they want to know when anything, not just the thing they're predicting, changes. When they want to know if what they're predicting changes away from normal, then that's change detection. So they want to be identified, hey, right now, I'm in a bad production state. That would be change detection. But once that change is detected, what they really want to know is why. And that is root cause identification. Change detection and root cause identification, although commonly confused, they're actually two completely different analytical methodologies. Our most forward-thinking manufacturers want to know how to run their best operation in its ideal state all the time using analytics. And this is called prescriptive analytics. When prescriptive analytics and closed-loop control are combined, you have the powerhouse of automation, and we'll talk about that more in a minute. Let's dig into each of these. Starting with closed-loop control. So closed-loop predictive control is different than your general APC that is attached to a subject matter expert derived static control loop. Those are great and they work for a lot of applications, but in predictive control, you want to use a real-time prediction for something that is hard to create a sensor for and integrate that into your control mechanism. So the most basic example I have for a paper maker is controlling a functional chemistry. So adding something like dry strength is supposed to heavily influence your strength lab test, but your strength lab tests only come every 30 to 45 minutes. They don't have online high frequency sensors. Even with the addition of an auto line, so maybe you get more testing, you still don't have the same frequency as you have with, say, your basis weight scanner at the reel. But they can be supported by a predictive model. So the predictive model can be fed into the controller, which knows the control limits of strength. It knows the minimum amount of chemistry you need to be pumping, and it can send a signal to the chemical pump, dosing the process to optimize the usage and avoid off-quality situations. So in short, you're creating a control loop, not very different than normal control loops, but you're using something that is difficult to create a sensor for. You're using a prediction for that instead, and controlling something like a functional additive, or think about furnish, maybe certain fiber coming in from a supplier A versus supplier B, so on. So the second method we talked about is change detection, which these methods, this is one of my favorite topics. Change detection has come a long, long way since center lines and Six Sigma control charts, both which are very useful. I'm sure many of you have implemented center lines or control charts. You've accompanied them with alarms. Then you were inundated with those alarms and promptly turned them off. We have way too many variables in our process to monitor using basic control charts and alarms. It makes it not useful. Our operators get very annoyed at a constant red alarm. Our email inboxes are full of center lining alarms. Anyone who's used the center lining software knows exactly what I'm talking about. Instead, change detection methods founded in predictive models can help us avoid those false alarms, because the prediction knows when our process truly shifts from normal. It's looking at, remember, 200 plus variables together, not just the 10 to 12 that we try to draw up control charts or center lines for. A methodological discussion really is out of scope here, although it could go on for days. We are going to release the paper that's behind this presentation. I think that it will be attached to the email send out at the end, so be looking out for some more details there. But basically, you create a predictive model using all of those variables that you'd like to monitor, and then you use that predictive model to monitor the process for changes. So change detection is really, really cool. Again, it really is my favorite of the analytical methods, but that's just because analytically it's a really neat process. However, once the change is detected, most manufacturers lose total interest in change detection itself because they want to know what the cause of that change is. And as I alluded to earlier, change detection and root cause analytics, which are obviously brother and sister, they're not the same. So root cause analytics, you can do this using a traditional approach. There are a lot of Six Sigma methods that help us uncover what could have been the cause to an issue we're having, like an A3 process, so on and so forth. Or you can use an analytical approach. So take, for example, the North American manufacturer who is struggling with broke utilization. What caused that initial low strength material to begin with that started that vicious broke cycle? We can detect the initial change using change detection methods, and then that triggers the use of the root cause analytical engine to pinpoint what caused that change using these analytical methods. So once the root cause is determined, analytical insights to the differences in the good and the bad production. If you're one of our customers already and you work with us, you've heard me say good versus bad a lot. But once we understand the difference between good versus bad, that can lead us to efficiently and effectively correct the root cause so that it doesn't happen again. And then on the right-hand side of this slide, the fancy Tesla edition, if you will. I'm not a car person, but I think everyone's pretty fascinated with Teslas. The Tesla edition of advanced analytics is prescriptive analytics. And this is what people think of when they think artificial intelligence. This is the method that can analytically tell you what to do to keep your process in its ideal state and when to do it. This is analogous to Google's turn-by-turn navigation that we all know and love. When paired with closed-loop predictive control, as depicted in the flow here on the right-hand side, that's when we have the self-driving car. I'm not sure if Tesla's self-drive, but I think they do. But if they don't, they will soon. So that's what I'm saying here. This is the Tesla edition. This is everything put together. And when the general population thinks about AI, this is what they think about. Google getting them from point A to point B using turn-by-turn navigation. You don't need to know the road conditions because the analytics knows the road conditions. You don't need to know how to drive a car if you're in a self-driving car. So your digital supplier, if you're a manufacturer who is already working in this space, should be able to offer you a path to these solutions. They're not out of reach. Companies like Tesla have shown us how they can push the envelope for using data and analytics and artificial intelligence to drive value, to drive innovation. But in the pulp and paper industry, which is arguably cooler than any car, your digital supplier should be able to offer you a path to these solutions that are specific to your problems in the paper industry. Our industry is very, very unique in the sense that none of our family members understand what we mean by we make paper. But our data is also different and complex enough that we need to use solutions that are specifically developed for us. The goal of all of this is to act on the insights that we capture and capture value, the insights that we get from this data. The capturing value part is a lot harder than it sounds. It seems obvious when you say, okay, I've detected the change, here's the root cause, but actually going to fix it so that it doesn't happen again, trusting the analytics that it's leading us down the right path. There's a lot of resistance to this. There's resistance to change. There's data security concerns. There's disbelief. There's a lack of corporate-wide support and so much more. If you're a manufacturer in the room, you're probably feeling some of this in your internal culture. How do we overcome this as an industry? For starters, we've really got to thoroughly develop our data strategy. And I don't have all of the answers, unfortunately, but the customers I work with who have had the most success have a few characteristics in common. Their companies work without silos, And that might be mind-boggling to some, but specifically the business, the operations, the IT teams, these folks are all connected and they share a common goal around a data strategy. Their key stakeholders and operators are data-driven. While they appreciate their subject matter experts and they lean on them heavily, they question everything and expect the data to support any claims. So they're basically looking for both sides of the story to match. They're also very, very agile in the face of obstacles. If their first plan they roll out doesn't work, they do not deem the project a failure. Rather, they pivot and relentlessly pursue success. They do this over and over again until they find it. For some, that takes a couple weeks. For others, it takes over a year. But once they all have an aligned vision to make better use of the data that they already have, and when they partner with the right supplier and they use the right technology to fit their specific needs in the industry, they do eventually create value from their data. It's not as simple as handing someone a cell phone who has never used a smartphone before, bless my great grandmother's heart, and telling them to go to the town next over using GPS. It's not that simple. We have to remember that we're starting at square one here. So it does take some time. But if you're relentless in your pursuit to find success using data, we have plenty of data and the methods exist to help us do just that. I'm obviously very, very passionate about this topic, and I definitely want to open it up to any questions. I currently can't see anything in the chat window, so I'm going to rely on Beth Ann to share with me any questions you guys have now. You can raise your hand and speak up, or you can type them in the chat box. All right, we have a hand raised, Beth Ann, right?
There we go. Yep. Go ahead.
Yes, good morning. Kirill Bayev from Wilmington Research Center. I have a few questions, Cydney, just to follow up on presentation. The first question is, how do we know if we are capturing all most critical process data information to start applying process analytics to analyze and predict the outcome? That's the first question.
Okay.
Do you want me to go through others or just kind of?
Yeah, let's start one by one because my mind might forget the first one. It's a great question. So the question is for just to repeat it, make sure I've got it correct. How do you know that you have enough data to enough good data to start walking down the path of using advanced analytics approaches or even just basic analytics in general? That was the question, correct?
Yeah. Yeah, and not just good data, right? Good data is important, but good, most critical process data.
Right.
Because what if we're missing some critical information that we are not aware of?
Right. Very, very good point. So a couple of things here. First is our data reach, if you will, in a mill or anywhere is always expanding, right? There are going to be new sensors created. There's going to be data that you want to add to your system, and that's totally normal and expected as we advance in technology. But with the data that you already have, if you have a historian, if you have a decently well-censored data, I always say that these advanced analytics methodologies are great for the brand new mill who has everything, but they're probably most value added for the like tier 2 older asset who is decently well censored but is just chugging along. And I say that because although they might not have all of the sensors, all of the data that you would hope to have, our data and our processes are so highly interdependent that even if there are 10 really important things and you've got 7 of them, I guarantee you that the analytics itself is actually going to make up for the loss of those other 3 just by understanding the relationships of the 7 that you do have. Because no, it's very, very rare to find one thing in papermaking that is not actually impacted by everything else. And I actually do get some challenge on this sometimes, like, oh, well, this chemical, this is, it only does this thing. Well, in order to do that, it affects drainage, it affects drying. It affects this, that, and the other. So all of those data streams that you have, even if you don't have, let's say, information at all about a chemical that you're adding, you're actually able to pick up on those relationships by using the right analytical approaches that don't just assume no relationship. You have to use methods that are built for pulp and paper making data, where every single stream of data is interrelated.
Mm-hmm.
Great. So your
Thank
next
you.
question? Yeah.
Yeah, thank you. Yeah. The other question is, prior to you applying the predictive analytics, and when you look at the available data, and this more around the quality of the data, how much data cleaning is required prior to starting application of predictive analytics? And really, it seems to be an ongoing process, right? Because you keep generating data while you're analyzing the data to draw the predictions.
Right.
And how is the cleaning of the data is done, especially with such massive amount of information that you are loading into the software? And is it what are the ways to ensure that the data that are loaded, so there's no 0 points, there's no negative points, that there are no some mistakes or outliers that are obvious or less obvious, to drive you to more quality predictions, right?
Right.
How's it done, really?
Yeah, great question.
Cleaning the data for us.
So I'm glad you touched on data cleaning, because this is something that a lot of people just skip in their minds in general, particularly like business leaders who are asking their data scientists to investigate something, or whatever that is. If you think of a problem, if, for example, if you're a paper maker and you know you're having this problem, you can feel it, boots on the ground, it's there, you know it exists, and you ask your resident data scientists to investigate the problem using analytics, they're going to spend 80+% of their time cleaning the data. And that kind of scares some people. I'm not saying cleaning it as in taking 700 data points down to 300. That's not at all the goal. But exactly what you're saying, the fact that there is such a high dimensionality in our data and high frequency. So if you're thinking about an Excel spreadsheet, when I say high dimensionality, a lot of rows from left to right. When I say or a lot of columns from left to right. When I say high frequency, a lot of rows from top to bottom. When you take a data set that large with that many different levels of influence, lots of opportunities for zeros or sensors to be off, it is really a very, very tough process to clean data, particularly ad hoc offline. Now, for our Solenis's online analytics solutions, which we called OPTIX, that was that screen that you saw when you first joined on, there's all of that data cleaning specific to our industry built in. So as the data comes in, it is cleaned effectively. And we spent months and months and months working with our strategic partner to get this right, because it is different in paper making versus oil versus e-commerce. There's different methods that you have to use. So rest assured that as far as the online analytics products that Solenis is offering you, that is fully automated. It's scalable. It's something we worked very hard on, and it's something we're still improving. It's never going to be perfect. Sometimes we do catch just an off-the-wall value that maybe was a poor sensor reading, or someone's finger didn't put in the decimal point when they were doing a lab test. Sometimes we do find things here or there, and we improve our processes just like any other thing. But it is a very, very important topic, and it's something that we had to do in a scalable fashion, so that, to your point, as the new data comes in, it is automatically joined with the old data and cleaned effectively. Ad hoc, though, very important.
Sorry, to kind of understand, what is the cleaning process, right? Who is doing it, and at what point in time, and how is it kind of correlated with what you're doing? As far as applying predictive analytics?
Yeah, sure. So I'm not quite sure if I'm answering the question correctly, but we Solenis do it in our product OPTIX. And by we work with a technology partner. We have a strategic partner. So it's like both of us together have developed OPTIX. So it happens automatically. The methodologies that we use are novel. It would be, we definitely talk offline and go into some of the details, but they're specific to our data, which is highly variable, highly interrelated, continuous time series data. The methods are novel. Some of them we created in-house. Some of them are basic methods, but together there's an algorithm that goes through step by step to clean the data. It's not something that we share publicly, but we do have some more information about it in this paper and also a previous paper. We can attach both of those to the email we send everyone afterwards.
Understand. Thank you. And what is the time frame to kind of learn the process and collect the information before you start to do predictive analytics?
So great question. The official time frame for OPTIX, like if you wanted to get an OPTIX prediction of strength or bulk or whatever it is in your process, it's 10 weeks is what we say. That's like the standard answer.
Sorry, can you repeat?
10 weeks is our standard
okay.
answer. Yeah.
Okay. Thank you.
Yep.
Great questions. So if anyone does have a question up, I see another hand raised. Go ahead.
Hi, good morning. I'm from Solenis, Hyderabad, India. So the question is related to the previous question. So you said about the cleaning of data. So the cleaning of data does include treatment, outlier treatment, and how do you treat the outliers?
Yes, so the data cleaning process definitely includes outlier cleaning. There are a lot of methods that can be used to clean outliers, and we use a lot of them. So it's not a one size fits all. It really depends on the data stream coming in and so forth. A lot of the methods are branches of like IQR, so interquartile range cleaning. But there are so many specific outlier removal. There's so many techniques. So again, we don't go into the details of them just because it's intellectual property to Solenis, but we can certainly chat offline and send the papers that have some more of those details in them. But great question. They're just for, maybe folks on the phone who aren't aware of how intense the data cleaning process is. It truly is 80% of any data scientist job is cleaning the data. And that's because it's not a one size fits all. Great question.
Yeah, thank you. And the other question is, as you said, there are around 200 fields. There must be some categorical fields, right? So, and how do you deal with the categorical data? I mean, is there any categorical data?
Yep, good question. So definitely there's a lot of categorical data. For folks on the phone who might not be aware of that term, categorical data is just basically use of categories instead of numbers. So the most appropriate category that we are all interested in is grade. So for papermaking grade specific data, each predictive model, each OPTIX, if you will, works on one unique machine for a unique grade. In some cases, there are opportunities to have sort of a master model covering a lot of grades, but one piece of categorical data that we deal with all the time is grades, and we treat it as a feature. So to answer your question on a technical standpoint, most categorical data in the predictive modeling that we do, we treat it as a feature.
Yeah, thank you.
It looks like we have another question. Go ahead. Karel, go ahead.
Sorry, I was on mute. Yeah, so Cydney, the question was follow-up question is, what are the limitations of this predictive analytics approach, and what we have to be aware of as far as the situations where it can work well and the situations when it may not work well? And maybe there are some gray areas. It may or may not work.
Definitely. So this goes a lot to the implementation and adoption piece, how important it is. So let me just hit some of the basics. These methodologies work really well for investigating, so predicting things around the end of the paper machine or the end of the pulping process. So things that happen after a bunch of other things happen. For example, predicting something like strength, predicting something like bulk, or anything in the quality lab, that's where these methods really work well. Or predicting something like kappa, predicting pulp brightness, predicting solids at some point further back in the process. So somewhere where you're predicting something that happens after a bunch of other things happen. That is where these methods work best. Now let's bring this so I can answer some of the where its limitations. Let's bring this to the paper machine just because it's easier for me to talk about that. This these methods, particularly change detection could, but root cause, change detection, prediction specifically will not do great in the time of a catastrophic mechanical failure. So if you have something that breaks off your asset, a prediction isn't going to know that's going to have happened, particularly if it's something to do with like mechanical degradation that happened really slowly over time, something due to long-term vibrational degradation that might not be seen as triggering to the prediction because it has such a small effect. Something else that we get quite commonly is, and it's not that these methods don't work well, it's that it's kind of pointless, predicting a break. So a lot of people say, oh, but if you could predict my break 10 seconds before it happened, and then ... They don't finish their sentence because what can you do with that information 10 seconds before your paper falls off your reel, right? So there are definitely some use cases of prediction in paper making that, not that they wouldn't work. One thing that does not work well is predicting catastrophic mechanical failure using a quality prediction. But something that is kind of pointless, even if you could and you can make a prediction that say will tell you when you're about to break off your asset. What's the point, right? Why would you want to know that? Instead, you would want to understand change detection. When has my process shifted? And you can start, correlating shifts in your process to increases in breaks. Well, then we've got something, right? Then we can use the correct analytical approach. So that's some of the limitations. And more broad limitations. Analytics is not the one size fits all for everything. And in fact, what I love about Google's turn-by-turn navigation is that when you arrive at your destination, it doesn't turn around and tell you, oh, oops, by the way, I could have saved you 2 minutes if you would have gone this other way 15 minutes ago, but you didn't know because I didn't know, so I didn't tell you. So you don't get that like feedback when you arrive at your destination on turn-by-turn navigation from Google Maps. It's the same in papermaking. So analytics does not catch everything. There is false alarms in change detection. There are variables that are selected as important to the prediction, like a tank level, that your brain, our human brains, don't understand, but that's okay because the analytics brain does understand. It can think in 200 dimensions. So, the limitations are, in my opinion, and just in my experience, not nearly as dreadful as the extensive value you can add in the process by using analytics to help, say, control something like wet strength chemistry to impact wet tear lab test values, so on and so forth. But there definitely are just the normal, hey, this isn't the end all be all. Hey, this can't replace your operator. This does not replace your lab tester. This just gives them another tool in their toolbox, basically, to do things more efficiently, to drive cost savings in a more proactive manner instead of reactive manner. I could probably go on for days, but those are the top ones.
Thank you.
You're welcome.
Just as a reminder, if you have a question, please feel free to open the chat window. You can do that by hovering over the screen, and there will be a little toolbar that pops up on the bottom. And in the space below there, you can, or in that toolbar, you'll see a message icon and a raise hand icon, and either of those will work. So if you have any additional questions, please go ahead and ask them.
Great, and I just figured out how to actually see the attendees too. I see some familiar names out there. Hi, Bill Haskins. Good to see you. Glad you joined. Matt, Paul, my lovely team members. Glad you guys could make it.
Good morning, Cydney.
Good morning.
Getting ready to go into a mill.
Well, that makes one of us. Today I am not. Haven't seen the inside of a mill since coronavirus.
Awesome. So I just want to give everyone, one more chance to see if we have any additional questions. All right, perfect. So with that, we'll go ahead and end a few minutes early here. I do want to say thank you for attending. For more information, please contact either your local Solenis rep, Cydney, or myself. You can find additional information, including some case studies, some technical papers. The white paper for this presentation will also be on solenis.com/optics. And then following this presentation, you'll receive an email with a link to the recording and also a link to the technical paper that's associated with this presentation. Again, thank you for attending, and I hope you all have a very great day. Thank you.
Thanks, everyone.
Thank you.